what I'll be talking about is the NIST aluminum ion clock. And I'm sort of lucky in some sense that I get to go after Peter to sort of benefit from some of the things that he already explained. We have very similar systems. But I'd like to point out that sort of a theme in this talk is that the aluminum ion clock wasn't really designed for measuring new physics. It's not particularly sensitive to things like variation of fine structure constant. But nonetheless, it turns out to be a very good clock. And in that context, we've been thinking about sort of things we can do. So I'll just give an overview of what I plan to talk about. I plan to give an introduction on the sort of status and historical status of the NIST aluminum ion clock. Then I'll talk about measurements that were done in the last couple of years with 2 generations of the system that have been used to do spectroscopy sort of at the lifetime limit, where we are no longer sensitive to laser phase noise and we can probe out to long probe durations. I'll then talk about the sort of ongoing systematic evaluation we're doing for our new system, which is based on a calcium logic ion. Then I'll talk about an overview of future precision measurements we'd like to do in this system. So the aluminum ion clock is sort of famous in some sense for being the realization of the mono ion oscillator that Hans Dehmelt proposed many, many decades ago. There was this prediction that a single trapped ion clock could be used to realize a frequency standard or an atomic clock with systematic uncertainty below a part in 10 to the minus 18. And 4 decades later or so, this was realized in the NIST group with the aluminum ion clock, which demonstrated a systematic uncertainty with the magnesium aluminum system just below a part in 10 to the minus 18. So I'll talk a bit about why the aluminum ion is a nice system and why we've sort of been able to achieve this. The aluminum ion clock is nice because it has sort of a 0 to 0 transition. It has a singlet S0 ground state and a triplet P0 excited state, which eliminates many shifts such as the quadrupole shift, and has a particularly low sensitivity to black body radiation, meaning that it can be operated at room temperature. And among sort of singly ionized or neutral atomic clocks, the aluminum ion has the lowest sensitivity to black body radiation. A problem here is that the aluminum ion clock has to be used in a quantum logic spectroscopy scheme like Peter was talking about. And the reason for this is because, again, we don't have a cooling or readout transition. In principle, one exists, but it's far in the UV at about 167 nanometers. So all our readout and cooling operations are done through a logic ion, either magnesium or calcium. So I don't think I need to spend any time to discuss this since we just heard about it. But the basic idea is that we don't read out sort of a bright or dark from the clock state. We instead drive a clock transition plus a quantum of motion, and then read out whether or not we have added that quantum of motion through our logic ion. And then another feature about this is that we use sort of a narrow or a much wider triplet P1 transition to do some state preparation and stuff with our on the clock ion directly. There's a big problem with trapped ion atomic clocks, namely that they have a single ion. And this offers a really nice degree of sort of decoupling from the external environment. But measurements can only be done on this one ion at a given time. And this is subject to what's known as the standard quantum limit, which is coming from quantum projection noise. And it's just telling us that there's some limit based on we either measure sort of whether we made a transition or not, and then we have to do one at a time. And it's basically shot noise in a quantum system. This limit is given by this relationship here. And I kind of summarized the parameters down here. The important takeaways are that it helps quite a bit to go to longer and longer probe times. So basically change the slope of our Allen deviation here, or our stability plot. And typical figures for trapped ion atomic clocks are some low power in 10 to the minus 15 per root tau. And for context, this is what was achieved with the magnesium aluminum ion clock. And it would take about 2 weeks to measure down to reach the systematic uncertainty of this that we claim of some part in 10 to the minus or below 10 to the minus 18. The problem of going to longer and longer probe times, of course, is that we're limited ultimately by the coherence of our laser, among other sources of noise. But the laser coherence has typically limited us to probe durations of about 150 milliseconds. And an additional thing to mention is that clocks tend to be most useful when they are used in clock comparison measurements. And doing clock comparisons on multiple clocks can pose some unique challenges. And that's what I'll talk about in this next section, demonstrating some new spectroscopy techniques. These techniques are called correlation and differential spectroscopy. Basically what this is doing is instead of doing a measurement where we have sort of 2 independent probe lasers for 2 independent clocks, we instead use probe lasers that are somehow correlated and then measure sort of differences between transition rates of our 2 different clocks. And correlation spectroscopy is done with identical clocks and is performed with a parity measurement, which I'll talk about in just a bit. And then differential spectroscopy is another technique that allows clocks at different frequencies to be compared, again, at the sort of lifetime limit where we're no longer limited by the coherence of our laser. I'll first talk about correlation spectroscopy, which was performed in our group with 2 different generations of the aluminum ion clock experiment. There's, like I mentioned, the calcium aluminum system and the magnesium aluminum system. And basically what we do is we phase lock these. It comes from one laser, but we phase lock 2 different beam paths to each other, and then measure basically whether one ion made a transition, whether both ions made a transition, or neither. And this is basically results in a parity measurement here, and we can add an additional sort of differential phase between these 2 and measure out this fringe. It turns out that the maximum probe time is set by the lifetime of the upper excited state. For aluminum, this is about 20 seconds, which means that the stability is maximized with a probe time of around 10 seconds. And so what I'm showing here in this plot is just different parity scans with different sort of parameters. There's a probe time of 1 second and 10 seconds. And as we go out to longer probe times, the contrast gets worse, although it's still there. And then additionally, there's this parameter C, which is sort of a scaling factor. And the measurements I'm showing here were all done with 2 completely independent clocks. But there are techniques to entangle the 2 clocks, whether they're in the same trap or in separate traps. And doing that increases this constant C from 1/2 to 1, and basically gives us a boost of a factor of 2 in stability. I'll show here just a brief sort of sketch of our experimental setup. These 2 systems are located in the same lab. You can walk between them, sort of stretch your arms out maybe if you're tall, go between these 2 systems. And then there's a laser in a different room that sort of comes in, and we split off the paths and stabilize them. And an important thing to note is that there's active magnetic field servos for each system. And one reason for this is that some dominant errors that can reduce the coherence, even though the laser phase noise is not the dominant one, is that there can be differential noise between the two systems, say from the noise in the fiber paths or magnetic field noise that acts differently sort of between these two setups. And I'd point out that this is also because aluminum has some nuclear spin, and that can give some magnetic field induced Dehmelt shifts. Here are some results from these measurements done a few years ago now, showing just the instability at 1 second with a turn up given by the laser limit, which I say again is around 150 milliseconds. And then there are additional sort of data points showing that this contrast can be extended out to something approaching the lifetime limit of 10 seconds or so. In practice, this ended up being about 8 seconds. This was limited by hydride formation rates in one of the systems. Collisions with hydrogen can form both aluminum hydride and magnesium hydride. This ended up being on a time scale of around 30 minutes. Something to point out though is that this reduces, if we're able to probe at the lifetime limit with aluminum, this will mean that we can measure down to our systematic uncertainty in a matter of a day or so, as opposed to 2 weeks, which sort of makes a new class of measurements possible if you're able to do things, sort of multiple types of measurements, scan over systematics and stuff like that. Just some more data here showing that contrast in these parity scans is maintained over long probe times up to 8 seconds. But some tricks did have to be applied. So during typical clock operation, we're just locking to a laser. We would probe on the outer Dehmelt states, so 5/2 to 5/2 nuclear spin transition. But instead, these measurements had to be done to get higher contrast by using an intermanifold transition, the 3/2 to 1/2 transition. And again, this is from differential magnetic field noise, which was a big limitation of these measurements. The next thing I want to talk about is differential spectroscopy, which was performed in using the calcium aluminum system and the ytterbium lattice clock that's also located at NIST. And this measurement is essentially the same thing as before, where we are comparing basically two different clocks directly without the need to sort of lock to a laser and then compare the lasers. The problem is that the ytterbium lattice clock and the aluminum ion clock are sort of pretty different frequencies. And in practice, they're also different systems. And the ytterbium lattice clock operates with a couple thousand atoms, has much higher stability. So basically, the way this sequence works is during a measurement, a Ramsey sequence begins sort of with the defined timing such that the sequence begins at the same time for the one clock system and the other clock system. And basically, we use the fact that the ytterbium lattice clock has higher stability. So we'll sort of complete that Ramsey sequence and then feed back onto the aluminum laser using the information we've gained from probing the ytterbium lattice clock. And it turns out that this group has made some pretty exciting developments. They've demonstrated a new 0 dead time lattice clock. And by using this 0 dead time clock to extend the probe time of the aluminum ion clock, they were able to fit in sort of many probes, maybe not many, but a few different probes of the ytterbium lattice clock, which again sort of pre-stabilizes the aluminum laser and allows this parity measurement to be performed. And these plots at the bottom are just showing sort of differential phase evolution of the two lasers, which can be overcome by doing this almost sort of cascaded spectroscopy sequence. I'll show again data that shows at different probe times here, just below a second and then up to a couple seconds, that this contrast can be maintained and optical coherence can be maintained up to several seconds, again with the dominant limitation being the lifetime of the excited clock state in aluminum, and subject to some differential, in particular magnetic field noise. And with these measurements, they were able to demonstrate about a factor of 10 improvements in stability. And doing this resulted in one of the, I think, the most precise sort of interspecies clock comparison that's been done to date. A big caveat, though, is that I mentioned that these measurements were performed with the calcium logic ion-based clock, and that clock has not had a complete systematic uncertainty evaluation performed. So both the correlation and differential spectroscopy measurements are proof of principle measurements, but have not shown clock comparisons with a fully realized uncertainty budget at the what I call the systematic limit. So I think it's probably not worth going into extreme detail on the things we've been working on, because this has been consuming quite a bit of our time recently. But I'll show just the uncertainty budget of the previous generation clock, this magnesium aluminum ion clock that had a systematic uncertainty just below 10 to the minus 18. And I'll point out a couple things that are different when we go to calcium. One thing is that we have the same problems that Peter was talking about, where some of the modes are very slow and couple very weakly to our cooling ion. And this is different in the case of calcium compared to magnesium because the calcium ion is just heavier. There are some nice features though. It's an optical qubit as opposed to a hyperfine qubit. The cooling transitions are much less than the UV, which should lead to lower first order Doppler shifts. And in the future, we can sort of use the calcium ion as a sort of well understood probe of various systematics. And just to point out some of the things that we've been working on is getting down our micromotion shift. We have a new trap, and this has been shown to perform a bit better than the previous system. This can be reduced by quite a bit. Quadratic Zeeman shift has been a bit problematic for us because there's no sort of pure magnetic field insensitive transition in calcium, or at least the calcium isotope we're using. And then background collisions in the first order Doppler shift will be different in this different system. So again, these are just some of the things we've been working on. The micromotion shift, quadratic Zeeman shift, and then background collisions are also different. So we've been working on this in the new system, and we've been thinking about different measurements that we can do once this has been evaluated. We want to sort of combine these long probe times. We want to combine this sort of very good uncertainty budget that we have. And we want to see if we can use this to do searches for new physics. And I'll talk briefly about what those could look like here. I think we've kind of been over what many of these would look like. The most relevant ones for us would be things that depend on variations of the fine structure constant. So say dark matter searches or slower variations of the fine structure constants. And there are also sort of precision tests of relativity and fundamental symmetries like Lorentz invariance, local position invariance. And I'll go through a bit of these and show how they're relevant to our system. For a while, about a decade or so, the aluminum ion clock was actually able to set some of the best constraints on slow variations of the fine structure constant. And this was done through a comparison of the aluminum ion clock transition frequency over time to the mercury ion clock transition frequency over time. But there's this term K that Peter was talking about, which characterizes the sensitivity to variations of the fine structure constant. And you can see that in this measurement, the mercury ion clock was sort of doing all the heavy lifting in this experiment. That clock has sort of been put out of commission at NIST. And our prospects for improving this would probably be, again, with the measurement between aluminum and the ytterbium lattice clock at NIST in sort of these differential spectroscopy measurements. I'd point out that other systems exist for this. In particular, the ytterbium ion clock at PTB has set very good limits. Their system is kind of nice in that ytterbium has 2 different clock transitions with relatively high K parameters here. And by doing clock comparisons between these 2 different clock transitions in 2 different systems, they were able to set pretty stringent limits on variations of the fine structure constant, also some limits on variation of the proton to electron mass, just by comparison against the fountain clocks. Or maybe it was the maser. Yeah, the maser. And then in addition, they were able to set some gravitational couplings, which are very interesting. The takeaway here is just the sensitivity to variation of fundamental constants matters a lot. And the aluminum ion clock is insensitive to a lot of things. And one of those things is this search for new physics. I'd point out another measurement that was done sort of across the city from us at Gila, which was done in Juni's group, comparing a strontium lattice clock against their silicon cavity, and basically using the fact that the silicon cavity, like was mentioned earlier, will have some length dependence on the fine structure constant. And in this measurement, like in the measurement I was talking about with the aluminum ion and the mercury ion clocks, it's the cavity that's really doing all the hard work here. And this is something we're thinking about trying with the aluminum ion clock, because we also have a cavity that we can use for this. And what's interesting is that they also mentioned that they're able to do some dynamical decoupling schemes to provide a bit higher limits at higher masses, higher dark matter masses. And we think that this is something we may be able to do by being able to probe at longer and longer probe times. We can fit in many of these dynamical decoupling pulses. And we've thought about sort of characterizing the laser noise to be able to do this in a competitive way. And then the last thing I'd want to talk about is just some things that we've been thinking about that I'd like to show very briefly, that show sort of a different way of thinking about clock comparisons. And this is revisiting an idea from our group that was about 10 years ago or so, where in a couple previous versions of the experiment, they trapped a logic ion, 2 aluminum ions, and using some tricks, they were able to perform independent readout of these 2 clock ions. And they were ultimately able to do this sort of correlation spectroscopy type measurement before the technology had kind of gotten there, just due to the fact that they were able to cancel out the laser phase noise by probing these 2 ions with the same laser. And then sort of differential noise was also eliminated just by the fact that these 2 ions are located in a very similar space. And we've been thinking about this measurement again because things have improved since 10 years ago. We have just better vacuum for one, so less collisions. And it'd be interesting to think about what sort of clock comparison measurements we can do by revisiting this idea of the 3-ion crystal. So just to think about this again, we have calcium logic ion, 2 aluminum clock ions, and then we can do correlation spectroscopy on these 2 clocks, measure this parity scan, and we'll ultimately read out the difference between these 2 clocks. Something that I found kind of exciting is the Weizmann Institute also performed measurements like this with 2 strontium ions. They were in fact able to entangle their two clock ions and perform a very competitive measurement of the isotope shift on these two strontium ions. And I think we'll be able to at least think about doing similar extremely high precision measurements using a 3-ion crystal and the sort of nice features that the aluminum ion clock has. And just two sort of ideas that we've been thinking about that may not be super interesting for a lot of new physics, but there's an additional clock state in aluminum that's very close to this triplet P0 state we use. It's the long-lived triplet P2 state. This has a lifetime of a couple hundred seconds as opposed to 20 seconds for the triplet P0 state. And we could imagine doing a very high precision comparison of the transition frequencies of this singlet S0 to triplet P2 and singlet S0 to triplet P0. And then another thing we could think about measuring is basically the difference in time dilation shift between these two ions, which, because it's an asymmetric crystal, is very slightly different. But again, this is just showing that we think it's worth thinking about this idea to make extremely precise measurements using long probe times and a fully evaluated uncertainty budget. And I'd like to just sort of close the story here by summarizing what the status of the sort of status and history of the aluminum ion clock experiments. We're able to do very precise measurements with the trapped ion atomic clock. With a single ion, the standard quantum limit imposes some pretty harsh limits. But by improving stability and going to longer and longer probe times, you can sort of work around this limit. And finally, differential measurements with co-trapped clocks are potentially a useful tool and I think worth thinking about. And thanks.
Thanks very much, Matt, for a wonderful overview talk. Questions for Matt? Thomas.
If you go back one slide, then to show the level scheme again, you mentioned at the beginning there's no cooling transition, but what about going from the triplet P0 to the triplet P1 and use the clock laser as a repumper in this case? And that should give you probably 20 seconds of cooling time, right? And probably with a very low Doppler limit because these transitions are rather narrow.
Going from the triplet P0 to triplet P1 or from the ground state?
No, not from the ground
I
state.
see. We've thought about it. This is not a particularly nice wavelength, so I don't think we've thought too much about it, but it's maybe worth thinking about going from the clock state to the triplet P1 state. The other idea was using sort of a 3-level scheme and going from the triplet P1 state to an upper D state, which then decays back down to a fast cycling transition. And this basically gives sort of a tunable line width transition. A big problem is just that the lasers are pretty UV.
There probably also be some higher triplet P states, right?
The lowest one is around 200 nanometers, and it's a D state that decays to a singlet P state.
I see. Thanks.
Over there.
So coming back to the slide where you showed the search for new forces using this cavity method and yeah, I was just wondering, maybe it's just a stupid question, but would this make any difference if you use cavity QED experiments to do such tests?
I have not thought about that, and I'm probably not the right person to ask.
So, Matt, I have a quick question on your correlation spectroscopy. If you could go back to this ADEF with the greenish data point exactly.
Sure.
So it looks like the scaling here is steeper than 1/2, which kind of points to a correlated noise? Were you able to identify which type of correlation this is?
I probably can't speak to exactly what this correlation is or why these points look the way they do. What the thing I can say is just that the difference between these two sets of points, the green points are what was actually measured, and then the people doing these measurements developed some sort of noise model, and that's what these blue points are showing here. So
thanks very much.